Okay, let's get started. So today we're looking at what's known as the fundamental theorem of calculus. So this is one of the big mathematical things. You also might see here referred to as the definite integral. Alright, so this is what it is. So we've got some function f(x), and if it is continuous between A and B, doesn't matter whether it's continuous outside of that, but inside between A and B, x equals A and x equals B, it needs to be continuous. And if f(x) is little f(x) is the derivative of some other function, big F x, big F dashed x. So the derivative of big F is little f.
So big F is another function.
So big F is the antiderivative of little f. So if you take big F and you differentiate it, you get little f. So big F, I'll write that, is the antiderivative of little f. Then, here it is, then the integral from A to B of little f dx is equal to the anti-differentiate. You get big F. Big F is the antiderivative of little f. And we use these square brackets and put the A and the B on the outside. And what that then means is that you put B into big F, find out what that is, and then you put A into big F, find out what that is, and subtract the two. So this is the fundamental theorem of calculus. And if you really want to know the proof on it, it takes a few pages. 523. All the way through to 525. So 3 pages worth of proof. If you're really interested in it. So this here is the fundamental theorem of calculus.
Is Alexis in this class? Alexis?
No, she's not in the class.
But she is in this, she's supposed to be here now.
She's in a study that I take the role for, but
okay, so she just does study.
I haven't seen her.
Okay, thank you.
She wrote past this before.
All right.
Don't rub off the lot. You can rub off one more line if you want.
One more line. All
Yeah.
right.
That's generous.
Yeah.
Who is that? We're about to find it out. Is that? Do you know
I mean, the
what
windows is a good idea.
Sounds like it, doesn't it?
This listening to your video is going to get demonetized.
All sorts of stuff going on the video today.
Always forget when you're recording.
Yeah, same. Same. I'm just munching on the
Wait, alright, so if we want to evaluate the integral from 0 to 1 of x squared plus 2x plus 1 dx, according to the fundamental theorem of calculus, we then
We're talking.
No, I did. What's her name?
read.
Lorraine.
We anti-differentiate this stuff. So, if we anti-differentiate x squared, it comes x cubed over 3. Anti-differentiate, that becomes x squared over 2x squared over 2 plus x. Now I'm going to put it in the plus c. It's not necessary, and the reason it's not necessary will become obvious later. Alright, so these two of course cancel each other out. So we've then just got x cubed over 3 plus x squared plus x plus c, 0 and 1. Alright, so that's this line that I'm just rubbing out now. The next line says you put b in that, and you put a in that, and you take this one from that one. So, put b, and b is 1, so I've got 1 cubed over 3 plus 1 squared plus 1 plus c, and from that we take away 0 cubed over 3 plus 0 squared plus 0 plus c. So here we've got 1/3 plus 1 plus 1 plus c, and here we've just got c. So that's 2 1/3 plus c minus c. The c's cancel, giving us 2 1/3. So, as you can see, as I said before, I was going to put the c in, and I said it wasn't necessary. It become obvious why, because when you get down here, you're adding it and then you're taking it away.
Is that the same for every?
It's the same for every. Right,
Wait,
so
what are we actually doing here? Are we finding the antiderivative?
No,
find the antiderivative, you go from there to there.
we're just finding
Is this just like
the area under.
And now we're substituting these numbers in.
So imagine you've got a graph, right, and you've got a curve,
Yeah.
and you're finding underneath the curve the area between like
Oh, we're
0,
still doing that.
0 and 1 in this case. But instead of just being like an estimation, this is like a precise.
We're finding that fifth under
That's what the meaning of it is, as Glenn has said. All right.
Come here. Reuse.
I'm pretty proud of myself actually. I'm gonna just take some pride in my actions.
Yeah, I'm just going to flex and do a couple
Can I rub that out?
Yes.
No.
Not all of it. Up until
All of it.
leave the part where you substitute the numbers in, please.
But maybe if you weren't flexing, you would have done
I would have got it done. You're probably right.
All right. Another
Or if I
example.
wasn't late.
Yeah, true.
Let's do will we do an exponential or a log?
log.
A log.
Oh,
All right, let's go a log.
I have heard far more than what I should have.
Alright, so this is 1 over something, so it's like 1 over x, 1 over u. Alright, u the -1. So when you anti-differentiate the 1 over, that's connected to
Log.
log.
Basic.
AC, yep. Yeah, not any log, it's log base e of 2x minus 5. Now I need something else in there as well.
Plus C.
No, don't need the plus c, we just figured out we don't need it, it's not necessary. Something to do with these two here.
The derivative.
1 over the derivative. Now, technically speaking, I should use
Modulus.
modulus instead of
No.
the brackets,
Will you lose marks if you use?
possibly.
Oh no.
Certainly will if it's a negative number.
So this is only applied with log basically?
Yeah, only logs. All right. So then, the fundamental theory of calculus says substitute 5 in, substitute 4 in. Yeah,
What's that you thing?
I was just talking about something that's 1 over, what it's connected to log to the base e.
Oh, okay.
Can you read that?
No, I can't read like what it equals, but I can.
It's u -1.
Yeah.
All right. So here with this one, we've got a half log to the base e of 2 5s are 10 minus 5 is 5, minus a half log to the base e, 2 4s are 8 minus 5 is 3. We can neaten that up by doing what?
Wait, where'd the E go?
Oh, forgot it.
Oh, okay.
Using my calculator.
What do you notice?
You can cancel that.
Half's a common factor.
So cancel that.
Now, what about this bracket here? We've got logs and we've got a minus.
You can put them together. in a
Put them
bracket.
together? Yep. So when we're subtracting
It's log base
e of
5/3.
503.
Do you have to take the half out if you need to see?
We have to take the half out before you can combine those, yes. All right, so you would be expected, if it was a short answer question, you'd be expected to go all the way to here. Multiple choice question could give you any. All right. So move on to what Glenn and Nicole were talking about, the area under the graph. So this, what this definite integral gives, as they said, is it gives you the area between the line, this line, and the x-axis between x equals 4 and 5. All right, so that's what it actually represents on the graph. I'm going to write this out.
Half of it, yeah. Yeah, get rid of it all. Oh, or a half.
Which half, the left or the right?
Oh no, so you know which half.
The board's looking a lot cleaner.
Yeah.
More important, I can't believe it's not that bad.
I did clean it.
Is this a new?
This is a blue heading.
Area under the graph, it should be a subheading, I suppose,
Subheading.
but I've made it look more important.
Actually, it's actually 10F, isn't it?
Is it?
Pretty sure.
Wait, what was the one we just did?
10E.
Yeah, actually, no, you are right.
I'm
Is it
right.
10E?
I'm
It's
right.
just, it's just
So
the
it's
same.
red.
Because Lorraine was like,
This is a whole different chapter.
no,
but
I
it's the
don't
same.
understand why we've just done that when we could have used what we learned next in what we've just done.
They're like,
Are
that's
you
all
going to
right.
write out the same things, isn't it?
She actually said the exact same thing to me.
I'm going to write,
Yeah, she just replied.
this gives you
Oh, wow. All the questions are...
the area under the graph.
So this is 10f.
Yeah.
Yeah.
So haven't I done
Kind of. I don't
Yeah, but we're doing it like precise instead of using squares.
Yeah. See, I didn't do it.
I'm going to write precise area.
Alright, so the line x equals a is a straight line up there, the line x equals b is a straight line up there, and you can see between the curve, the x-axis and x equals a and x equals b, that forms a little four-sided figurey thing. And so the integral gives us this area in here. So on the graph, that's what it represents. Now, the only thing you've got to take care of is that there's area above the graph, but there could be area below the graph as well.
Can we put a ruler over there?
So when you do this, if the thing is below the graph, your area will come out with a negative. So the negative, all that represents is that the area we're talking about is below the x-axis rather than above. So when we're talking about area, we would then ignore that negative. All right. When we talk about area, area's got to be a positive number. We ignore the negative in that. When we do the area, it's not because it's unimportant or anything like that, but it just tells us that it's under the graph. Now, if you were doing some sort of kinematics or something like that, then that would make, in physics, that would actually represent something else. But for us, what we're doing, the negative just means it's under the x-axis.
I'm glad you added that to confuse me, Mr. Smith.
Hey?
I'm glad you added that to confuse me.
Well, you don't need to worry about it.
Just saying if it's a negative, just make it a positive. If it's a negative, then you've either done something wrong. Yeah, well, you've probably done something wrong.
Negative area.
I just got like kinesthetic stuck in my head and I'm like, what the fuck's that?
Okay, so if you
No, I really
put
don't.
them together and you get a negative, then just make what was,
Yeah, I get it, make it a positive. I
and
get
then
it.
make it a negative. And then you just get positive. That was pretty close.
We're making progress. No. I'm just always reading it right from the
Alright, so something like this, for example. So we've got something there like that. That there. When you do that calculation, you'll get a negative answer. Alright, just because it's below the axis. And seeing as negative area doesn't make sense, so we ignore the negative. Now, sometimes that means we've got to split it up. So if it's all above and it's all below, that's easy. But if you've got a curve where you've got some above and some below, that means we've got to split it up. And we'll talk about how that here's an example where we would have to do that. So I've got something there like that, and here is A and here is B. So between x equals A and x equals B, curve and the x-axis, these are the areas. Now, the mathematics, when we work it out, we get a negative for this bit and we get a positive for that bit. So the mathematics doesn't know in the end what it is we're trying to find out. The mathematics just works the numbers. So if you just do the integral from A to B of this function, you unfortunately won't get the right answer, because the mathematics sees this as positive, this is negative, puts them together. So what we need to do is we need to split it up. So what we need to do is we need to know this point here. Where's the red pen? It's supposed to be new. We need to know this spot here. Alright, and we need to then split that integral up into two parts, from A to C and then C to B, so that we can take into account that negative. Alright, so what we need to do is the integral from A to B of fx dx. We need to split it up, make it the integral from A to C of fx dx, and then from C to B of fx dx. Now we've also got to then remove that negative, because if I work out this as it is, I'm going to get a negative answer because it's below, and I need to remove that negative. So one way you can do it is by put those modulus signs around that and say ignore the negative. There is another way that you can do it. Or you can just put a negative in front. Because this will become negative, this will be negative, this bit. Put that negative there, negative, and negative, positive. These variations of these things are a favourite multiple choice question. There is another one as well. Or, the other way you can get rid of the negative sign is you flip these things around. So you go the integral from c to a of fx dx.
Do we need to know all of them?
Yep.
Hmm.
Multiple choice question. Favourite multiple choice questions.
Do we do any proper questions usually with this stuff?
Well, when you're doing a worked question, it doesn't matter what you use. But for a multiple choice question, favourite multiple choice questions, they give you a graph like this. Which one of the following could be used to work out the area between the blah blah blah? And so you don't know which one of these three
You're going to throw at you.
they're going to put. So you need to be able to recognise it. In terms of when you're working it out, doesn't matter which one you use.
No.
All right. So these three things here, they're equivalent to each other. All right. And what are they doing? They're turning that negative into a positive. All right. One example. Can I rubble that off?
Not the variance at the bottom.
Rub the top.
Yeah.
So do we get our summary book on the which exam?
Calculator.
Exam 2, calculator 1.
So the hard one's one where you
Yeah,
don't have
that's
to summary book or a calculator.
stupid.
That one only goes for an
Oh,
hour.
multiple choice.
So you only spend an hour wanting to claw your eyeballs out. As opposed to like 2 hours.
I don't know.
Or spend an hour sleeping.
Yeah. I reckon the calculator one looks worse though.
But I have not looked at either.
Yeah, I don't think anyone else has done any past
Alright.
exams.
This is a really bad diagram. Really bad diagram.
What was that noise?
I don't know.
Alright. So because we've got a bit below and a bit above, we need to know what this point here is. And given that the parabola is x squared minus 4, that x-intercept will be 2, yeah. Alright, so the area that we're after will be the integral from 1 to 2 of x squared minus 4 dx plus the integral from 2 to 4 x squared minus 4 dx. Now we've got to then change that negative. So this first bit will have a negative, so I'll just use that version there. Doesn't matter which one you use, that will do. And now we do the calculation. Alright. Antiderivative of x squared is?
Oh.
X3 on 3.
Antiderivative 4?
4. Shouldn't it be 4?
Yep, should be.
Huh?
Thank you. Alright, now we stick the numbers in. 2 cubed on 3 minus 4 times 2. From that, take 1 cubed on 3 minus 4 times 1. And then over here, we've got 4 cubed on 3 minus 4 times 4. And 2 cubed on 3 minus 4 times 2. Next line down, we've got 8 over 3 minus 8 minus 1 over 3 minus, and the minus is plus 4. And that we're taking away. We're taking away 4 cubed is 64 minus 16 minus 8 thirds plus 8. Alright, then there's a lot of mucking around here. So we've got 7 thirds minus 4. And over here we've got 64 take 8 is 56 minus 8. Alright, so 7 thirds minus 12 thirds should be minus 5 thirds. (56) minus 24 is 32 thirds. What have I done? Oh, it's not minus, it's plus, isn't it? Sorry about that. I just put minuses here, should be pluses, shouldn't it? We're adding those two things together, not taking them away. All right, so what do we do with the negative 5 thirds? Make it positive. So it's 5 thirds plus 32 thirds is how many thirds?
Worse and worse.
37 thirds square units. It's just a lot of number crunching. Great idea, Nick. Great idea. From here, use a calculator. There is absolute value. One of the templates is an absolute value template in your calculator, in your keyboard. So you can do that. Have it in standard, then it will give it to you in exact value.
You can do the whole thing on calculator. They've got a template for everyone.
you can actually do the whole lot on the template. You can go from here. There's a template, so you can go from there.
It's great.
Is it likely
Because
that
they're
that
gonna
would be
get
on the
this
non-calculator?
There could be a simple one on the non-calculator, yes.
So they can bounce the envelope.
Yeah.
There's someone
No.
There could be something like that on the
Yeah.
non-calculator, yeah.
Where are these?
All right, anything further?
That's all?
No more from me.
I was so confused, should I realise it was fuzzy in here?
This isn't where it's curvy things like a
Right,
Oh,
I'll come and show you.
calculator. Really? Yeah.
Math 2?
Yeah.
Yeah.
Oh, is this it? Yeah. So then you.
All right, so this is exercises 11E and F.
Really loving the research of my now. It's great. It becomes socially acceptable.
On your
Yes,
work plan.
cognition work, because
So we'll get this stuff all finished this week.
So I've just been crying.